My name is Sir Arthur Stanley Eddington. In this particular project, I was to measure the apparent position of stars versus the actual positions during a total solar eclipse in May 29 of 1919. Therein lies the problem with proving relativity. The conditions limit your ability to test it. Einstein had offered proof for relativity by calculating the nearest distance of Mercury to the Sun, which is the perihelion. Einstein insisted that had his method for calculating this perihelion been wrong, the light proven not to be deflected as much as predicted, or the absence of the gravitational redshift, as he called it, would disprove the entire theory of relativity. This particular proof that stars' lights would be shifted due to the sun's gravitational field is the one I wanted to tackle. It is worth noting that Newton also thought that light would bend in a gravitational field, but by only about half the amount that Einstein predicted. So we were to use the best telescopes possible and follow the stars rather than the sun's path in the sky, as had been done in the past. Grab my tea here. Thank you for putting the cream first. Anyways, it is important to note that I measured the real position of the stars months before the actual eclipse occurred so we could test them against one another. So what were we actually trying to find or to accomplish, I guess, with this? As I said, we were going to be observing apparent position of stars versus the actual position of the stars. Okay, so essentially by proving that their position was different than it seemed to be, we could prove that the gravitational field of the sun deflected their light on their path to Earth. If space-time is bent by the sun's large mass, it makes sense that the light from these stars would follow its path. Now, we needed to test the stars that were closest to the sun, since obviously their light rays would be bent the most compared to the ones farther away. This particular star cluster was called the Hyades cluster. It's Greek. The obvious problem with measuring stars that are very close to the sun in the sky's position, the sun is quite bright, and so you can't truly see them or measure those things. So for this reason, we wanted to photograph their position during a total solar eclipse. By photographing these stars, we were able to calculate whether or not Einstein's suggestions were correct. To do this project, we needed to be in a good place. So I led the team to a small little island called Principe in West Africa, off the coast of West Africa. This island offered perhaps the best view of the stars for the maximum amount of time during the solar eclipse. We did have another team who traveled to southern Brazil to take measurements in case the weather did not cooperate. It is a good thing we did because the weather was not great. It seemed as though it was going to be cloudy. It was for a large portion of the day, but we were able to enjoy the sunshine, by which I mean absence due to the eclipse, and take our measurements. The island was treacherous itself, a lot of extreme conditions, weather, mosquitoes, predators, etc. The Brazil expedition also experienced extreme heat, tropical heat waves. In addition to the larger telescopes, they also took a smaller 10 centimeter telescope as a backup, and it is a great thing because the temperatures seem to have warped the metal in the larger telescopes. And I didn't really even get to watch the eclipse because I was so concerned about taking the photographs, and the clouds had just disappeared just in time for us to take the necessary photographs. So think about this world in 1919, March 29th. The World War I had just ended. I barely avoided conscription to service myself, being a good Quaker. I was a conscientious objector. However, working, I was able to avoid with my connections to Cambridge there. Um, and particularly this role in measuring these things. So in 1919, the world was still reeling from a large scale war, basically a world war, and so um, there there had been many advances in the physics realm. Einstein had come up with a theory of relativity. However, remember that um, the German powers were not trusted. German scientists were not trusted um, due to this war. So this strange kind of time in the world, and so I set out to prove this. And so his theory of relativity came out. His final theory, final form, I guess, in 1916. Einstein did, and so this is also quite fresh. And so women did not even have the right to vote in the world at this time in the United States. So it's a tumultuous world, and there's a lot of mistrust going towards the Germans. As far as colleagues in this, Einstein wasn't directly involved in this project, but it was his theory that was the motivation for such an expedition. Sir Frank W. Dyson, the British Astronomer Royal, was the man with the idea of the expedition, though I agreed to lead it. And Andrew Claude de la Chaux-Crommelin led the expedition to Brazil. He was a fellow worker at the Royal Greenwich Observatory, so we had crossed paths before we knew each other then. And likewise, we had crews to help with the experiments, but I would say that Dyson was the main guy with the administrative duties, and I was probably the major overseer. Later, there would be other observations of solar eclipses to measure the same thing, and they all gathered similar, if not more precise data. One man of note, William Wallace Campbell, who had done previous research on the subject, was a doubter of Einstein, and particularly his theory of relativity. Well, he performed a similar test in Australia in 1922, 3 years later, and his measurements of the stellar displacement were 1.72 arc seconds, plus or minus 0.11. And so with this new evidence, Campbell changed his mind on relativity and admitted to as such. So I was to lead the expedition to Principe, and I was the organizer largely, and it was also I who was primarily responsible for overseeing the collection of data, the measuring, and the publishing, though Dyson was definitely involved. Again, he had to be the one to promote the trip, and the measurement of these particular stars was his idea to begin with. He came up with the idea of these particular stars during one of our brainstorming sessions. I was lucky enough to be able to lead the expedition and to work with Dyson to pass the results and to publish the data. So let me be clear, my project was not to come up or develop the theory of relativity. This mission was simply to offer proof to the theory, to help prove this theory. So there was some doubt related to the observations from the Brazil team, and the telescopes had been warped a bit, but my findings were largely accepted as proof of this theory, and the results were solid enough for most, but Dyson offered to send our original photographs to anyone who wished to review them, or at least copies of the photograph. In a more broad sense, the media really took off with this, and really Einstein was thrown into the spotlight, and I suppose this really helped his notoriety, his status, I guess, really skyrocketed with this. I was chuffed with the information that I gathered. I think it's safe to say that the findings of the project really helped to win over the skeptics about relativity. Though there were some doubters. Like I said, I was pleased with the results and the findings. We did debate for a bit, Dyson and I, about the exact numbers because there was some discrepancies. The Brazil team's telescopes were a bit muddled in the. So again, I there were a significant number of scientists, and still are today, even who insist that my data was simply gathered to prove the theory of relativity rather than to actually test it. And I disagree with this. So I guess that leads me to my next explanation of why I would, or how I might account for the discrepancies. Um, and was I convinced? Yes, I was convinced. And Einstein's theory did predict um, a, a, a bend, a shifting of 1.75 arc seconds. And my photos that were able to be used from Principe measured about 1.61 plus or minus zero point 0.3 arc seconds. And the photos from Brazil seem to indicate 0.93. Though these results were hard to parse because the telescopes were a bit warped, and so the measurements from Brazil were actually closer to the Newtonian model, I guess that you might say. But the smaller telescope from Brazil did measure at 1.98 plus or minus 0.12 arc seconds. So the smaller telescope was close to what Einstein predicted, and also it was more precise than the other measurements. So for me, that was good enough, and we needed to be precise. And so Dyson and I decided on a measurement of 1.64 arc seconds, and so that was close enough to the relativity model, I believe, to offer some valid proof. Again, I still published the results from the other telescopes, and Dyson offered to send the copies of the original photos to anyone who doubted or who wished to review them. And I think that alone should disprove any notion that I simply performed this experiment and doctored the results and to reflect a proof of Einstein's theory. And I think that I was validated later on, vindicated, because the later expeditions proved much the same. So, okay, thank you for having me, and it was a pleasure to be interviewed. And